All right, so thanks for your lecture. And now we're
Of
going to
course.
have a discussion with some questions about various points that came up. So I'll start off with a kind of joke question. You were saying double chevron. Is that because you're from Detroit?
Exactly. Yeah, that's exactly right. I've got to represent for my people back in Detroit. So yeah,
Oh,
that's it's a subtle hat tip to them. So nice catch.
okay. Um, so um, you were talking about the at symbol for matrix multiplication in the class. Uh, I think we're using an older version of Python, or at least the book that we're using. It's called Computational Physics with Python. I think it's with respect to an older version. The command we use is dot. Is that compatible with CVXPi? Do you know?
Yeah, in fact, using dot and the at should be there shouldn't be any issues there because I think underneath the hood, the dot method is implementing essentially well, as long as the NumPy version that you're using is new enough to support this convention, then should not have any problems whatsoever. So you should be all good there.
Okay. Okay. So then you were talking about, uh, in SDPs, maybe scroll up a little bit to
Sure,
your,
yeah,
yeah, that's fine right there. Go down a little more where you show the whole, yeah,
sure,
that
yep.
one. So you specify the variable with cvxpi.variable. And then I know in MATLAB, you can say like assign different types, like
Mhm.
non-negative. You can say semi-definite. You can say complex semi-definite. Are those options available? Do you know?
Yep, exactly. Those options are available. And in fact, I could have, one thing I could have done for this variable, instead of, let's say I wanted to enforce, like if I go up to this problem up here. So I wanted to enforce that X in this case was positive semi-definite. And one thing I could have done instead of, excuse me, adding to the constraints like I did here with the hat tip to Detroit double chevron, I could have just specified inside of the definition of the variable the optional parameter. I believe it's semi-definite equals to true, but it's all in the documentation. So either one of those would be equivalent ways of enforcing that the variable is positive semi-definite.
I know in MATLAB, if you just put semi-definite, then it makes it a real matrix. And then that's actually tripped us up in the past. We in quantum information, we always need complex semi-definite. So anyway, it's all there in the documentation. It's good
Yeah,
to know.
exactly. And a lot of the, oh, go ahead. Yep.
Oh no, go ahead.
I was going to say, yeah, I've been tripped up by that too many a time, both
Yeah.
in Python and MATLAB. So I have yeah, scars for that. And recently, I think some of the support for some of the more complex valued things that you can do in CVXPi have been kind of more supported than they were in past years, which is kind of why I started doing some of these things in quantum information using CVXPi because some of the support just wasn't really there before, but it seems like there's a lot of more recent developments with more people in quantum information that are kind of pushing for these features to be implemented, which is kind of nice.
Oh, that's excellent. Okay, so then now my next question is about the constraints. So maybe scroll down a little bit.
Yeah, I can.
And it's just a curiosity.
Mhm.
So the variable constraints is a list. It's a Python list.
Mhm.
And then you're appending items to the list. And then I'm just curious, like, what is the type of, like you have constraints that append, and then
Mhm.
you feed in you write x var equals NP identity.
Mhm.
What is the type of that? Do you have any idea?
I think there's a built-in class in CVXPi. I believe it's called constraint. So basically, it'll underneath the hood, it'll process each of the elements in this list, and it'll pop on, each of these elements, and it will construct a constraint type object based on, whatever element in the list it's processing. So
So
what you can,
CVXPi is interpreting this.
yeah, CVXPi is interpreting this. That's right. Yep.
It's interesting because I guess that's a consequence of importing CVXPi, right? Because like constraints itself is just an ordinary Python list, right? And then the other commands, like you call CVXPi.maximize, so it's part of CVXPi. So it's
Mhm.
just interesting to me that CVXPi steps in and interprets that part.
Yeah, I don't exactly know how it's done underneath the hood, in terms of like whether or not they do what they can do is they can actually, I've seen this happen before where they can just convert like verbatim the elements inside of the list to like a literal string and then just process those in like tokenize them in a way where each of the elements correspond to certain things that CVXPi knows what to do with. And then if they, if it pops on something that it doesn't really know how to process, it'll just say, you've provided me an ill-specified constraint. But what's kind of nice is this is something that I don't quite know fully. I'm just kind of speculating there. But I agree that it's a little bit weird, right? Because this is definitely a CVXPi thing, and then these are sort of like elements in a list that CVXPi like processes underneath the hood. So a little bit weird, but it kind of is a little bit nicer because you don't need to have that extra boilerplate code to convert it to a constraint. You just kind of
Mhm.
add it to a list.
Yeah,
So it's nice from a user perspective.
good. And then this is just a curiosity. So it's a little funny to me that we use the double chevron symbol instead of greater than or equal to. Um, I guess once you get used to it, it doesn't matter. But like in MATLAB, you just write greater than or equal to. Do you have any idea what's going on there?
I think it's a few things. I've heard that the greater than or equal sign is, I mean, more generally, even in the mathematical context, is kind of an abusive notation. So I don't know if the developers were like, oh, let's not use that because we want to use something that's like explicit, it's like a little bit different than that. Or if they just said I don't think you can, I'm not sure if this is also true. I don't know if you can also do this. Oh, maybe you can. So I guess maybe
Oh,
it's one or the other. So if you're used to that, I suppose, and if you prefer like, hey, I just want to do greater than or equal to. So scratch the first speculation that I had in my head where they just
mhm.
had some problem with the abusive notation. I guess they don't. So I guess you could do one or the other. So
Okay, that's good to know. Um, all right, so I have another I have another thing, but I'm just going to ignore that because it's kind of a trivial thing. But one thing I was wondering about is in CVXPi, or at least CVX in MATLAB, you can include functions for norms in
mhm,
the optimization task. And so
mhm,
I'm wondering if, like, I noticed when you call the trace function,
mhm.
if you go, oh, you have it right there,
Yep.
CVXPi.trace. Does it have a norm function as well?
It does. Yeah, there is a CVXPi norm. There's obviously the trace, and basically anytime, like there are also norms for like NumPy or NumPy provides you with norms as well. But when you're passing things into a maximize class here, you'll want to make use of the CVXPi version of that. Um, so that's why I'm not using like NumPy also provides you the trace, but in this instance, we're taking the trace of a CVXPi variable. So NumPy doesn't know what to do with that. NumPy is like, I don't know how to take the trace of a CVXPi object, but CVXPi does. CVXPi is like, oh, I know what this means and can interpret it properly. But yeah, so to answer your question, there are built-in methods for the trace, the norm, and the different norms that you might want to include.
Okay. Another question is in quantum information, especially, we're always doing things like partial trace, partial transpose. Does CVXPi have functions for those? Or alternatively, I think in your Taquito package, you enabled this.
Mhm.
You could comment on that.
Yeah, there are unfortunately no implementations that I know of that are standardized in either CVXPi or NumPy or anything like that for partial traces and transposes. In, like you said, Taquito. So if I go there, um, there's kind of a few things that might be of interest to people who want to use these functions for quantum information purposes, or I don't know any other context in which these would come up, but essentially if I go to, I think it's, so if I go here, there is sort of the partial trace function that is implemented, and this also works on CVXPi objects. So if you wanted to either perform the partial trace kind of in isolation on just a NumPy matrix, cool, you can do that. This function that I've coded up also supports essentially instances of CVXPi variables as well. So if you want to essentially do something similar to like let's just say in your objective function, you want to take the trace. Normally you couldn't do that if you just implemented it in vanilla NumPy partial trace, which you'd have to implement or roll your own or find a third-party implementation. But in addition, most of those implementations, or at least all of them that I'm aware of, don't support CVXPi variables. So if you use Taquito and if you want to make use of partial traces or transposes, those things kind of allow either NumPy objects or CVXPi objects. So that might come in handy for those types of applications.
Would you mind to, I know recently we were corresponding about an SDP for fidelity of quantum channels, and then you added that to the Taquito package. I believe that involves a partial trace. Would you mind to show us the document? I think you had some example, right? Like you had
Yeah.
the README file. Like this stuff here gets translated to something readable, right?
Um,
Oh, you have the code right
yeah,
there. I see. It's pretty
I
simple.
hope it's readable.
Oh, it's
Otherwise,
readable. Oh, yeah,
I'm a
sorry.
terrible programmer. But this, yeah. So this is one of the examples listed in the end of the notebook that kind of showcase some of the instances of SDPs inside of Taquito. And so you can see, so in Mark's paper, he has sort of an implementation, a definition of this channel fidelity between two quantum channels. And so one of the things that I did based on his recommendation was, take this, implement it into a piece of code, and, give the user the opportunity to, numerically solve this. And you can see that there's usages of, CVXPi, and then there's a partial trace here. So you can see that I'm making use of the partial trace function, which is imported from Taquito. So I'm using my own partial trace function, which again can lend itself to either being applied to CVXPi objects or NumPy objects. So you kind of got the best of both worlds there.
Cool. And just to reiterate, you said you had to do special things to make your partial trace function compatible with CVXPi. And then just my own curiosity, CVXPi.real, that's taking the real part of the matrix.
Yeah, that's my understanding. That's taking the real part of the matrix. Yeah.
Okay, cool. That's very nice. And then the final thing I'll say is you were saying like, why would we want the SDP for fidelity? Well, the channel fidelity is an example where the function for the fidelity of states is helpful, because then you start from that and you get a semi-definite program for the fidelity of channels, which involves an optimization. And so you're kind of forced to go to semi-definite programming, right?
So yeah, that's a justification for implementing the fidelity function in an SDP. So and I didn't mean to throw you under the bus there in the early part of the talk, but
Oh, that's all right. All right, so those are all my questions. Does anyone else have questions that they wrote down? Okay, so there's a question in the chat. Jack was asking, can semi-definite program be expanded to multi-dimensional inputs?
Let's see, multidimensional inputs. So like the variable here, like oh, actually that's a good question. And if you want some examples on multidimensional inputs, there's actually a very good thing to check out, the Taquito package, which I've had to come up against this.
So Jack, do you mean like multiple variables? Because like the variables involved, they are matrices, so they are multidimensional. Could you clarify your question a bit?
Like a three-dimensional or like an n-dimensional. Uh, I'm just thinking for applications outside of quantum mechanics. So
Sure.
I'm not sure if it's really applicable outside of quantum mechanics, but
Oh, it
just seeing
definitely
if
is. Yeah, so that's what we were saying last time in the lecture about the theory that semi-definite programming is used across the board in mathematics, engineering, computer science. It's not just a quantum information thing. And so, you know, the form of semi-definite programs that we were discussing, it's very general. And so like the matrices can be of arbitrary size, right? But it's going to get harder to solve as the matrices get larger. So like, Vincent, maybe if you have it, go back to the documentation for CVXPi.
Sure.
That one example.
The SDP example, right?
That's right. Yeah.
Cool. Yeah, this one right here.
Yeah. So here you see like, I guess there's multiple constraints and X is a matrix, right? So it is multidimensional.
Well, so I think I kind of understand, at least the way that I'm interpreting the question is like, if it's not just a matrix, but it's like a list of matrices, or like in the case of the example I was looking for was kind of this hack. So I think the question is if you have like a list of matrices or a list of matrices, basically what you can consult in the Taquito package here, and there's a comment right above here, which basically the CVXPi doesn't support optimizing over three, maybe it does three, but certainly not four-dimensional objects. So the hack that I have to overcome this is construct a dictionary. So a dictionary in Python of CVXPi variables, and basically just construct, you can see here, I'm creating this CVXPi variable of a given, of 2 dimensions, but this dictionary here has 2 extra dimensions. So I'm kind of adding however many dimensions I need for any multi-dimensional variable that I want to optimize over. And you can also see, back to Mark's question earlier about whether it was positive semi-definite or whatever is the optional parameters. I guess PSD is the optional parameter for a CVXPi variable if you want to specify it to be positive semi-definite.
And that's actually complex positive semi-definite?
Yeah, this is complex positive semi-definite. Yep.
Okay.
Yeah, so it's kind of hacky because I think in MATLAB, Mark, you can correct me if I'm wrong, but I think you can have as many dimensions as you like for the variables that you're optimizing over. So it's kind of annoying to have to do it like this, but it's possible. It's definitely possible.
I actually don't fully understand what you mean does not support optimizing over four-dimensional objects. Do you mean like a list of a list of a list of a list?
Yeah, so if I did this, I
Oh.
couldn't do that. Like if I had is that kind of what you mean? Am I understanding that question properly?
Yeah, I was thinking, I'm sure you've learned about it, but you know, like the target, I don't know, blanking on the word, the optimization problems where you have like an n-dimensional list and you know, do a priori kind of applications. I'm blanking on the term for that, but seeing if, you know, this would be a possible way to solve or optimize those relations. So yeah, this would be, you know, however many. So yeah, like 3-dimensional, 4-dimensional.
But there's no restriction on the number of CVXPi variables you can have, right?
That's true. There's no restriction on the number of CVXPi variables you can have. There's just the only restriction that is in play here is how many dimensions that particular variable supports. So for instance, this thing here, and maybe I can't write in this, but that is, if you're familiar with like the probability kind of marginal, you know, this is the way that you can specify. I'm going to start talking in quantum stuff now, but like the matrices that correspond to the probabilities for non-local games, where you're given like questions X and Y, answers A and B. And these are kind of like a list of matrices that are indexed by X, Y, and A, B, if that makes sense. So you can definitely support those. It's just they're not supported natively.
Okay,
Okay, cool. Thank you.
nice question. Are there any other questions? All right, I'll go in once, go in twice. All right, I'll hit stop
So,
recording.
well, I have a question, but it's not really so much about implementation, but more about theory. So I'm not sure if you want to field this off to Professor Wilde, but so what does the solution like kind of mean? So what would be the difference between like in your trivial solution of the where the answer was 4? Like what does that imply? Like I know it's the trace, but in terms of like a more real worldy kind of application, I'm not sure if that question's even answerable, honestly. But
Do you want to tackle that one, Mark?
You gave an uncomputable question. No, we'll try. So I think Vincent was just trying to show in some kind of trivial example, like this particular SDP, I would say has no real world application, right?
yeah,
It was just meant to illustrate on a simple example. And then the fidelity of quantum states or fidelity of quantum channels is much more interesting calculation. Semi-definite programs can be used for like portfolio optimization and finance. I think maybe it's even a linear program. I don't know exactly. And those things, of course, have real world applications, right? And then in the class, we talked about like finding the ground state of a Hamiltonian. You can write that as finding the ground state energy of a Hamiltonian. That's an important problem in physics, and it can be expressed as a semi-definite program, subject to some constraints, So yeah. And then if you were to open up the book of Stephen Boyd and his co-author with last name Vandenberg, I think they go through all kinds of examples of real world applications. That's a free book. I believe it's called Convex Optimization, right?
I think so. And on top of that, this examples page is really great. If you want to see any like more real world applications, like here's portfolio optimization, some model fitting stuff, some machine learning stuff, more finance derivatives. So there's a lot of different applications that you can check on this examples page, which are really cool.
Yeah.
yeah, I think like that least squares example is kind of what I was leaning towards with the n-dimensional kind of thing. So yeah, perfect. Thank you.
Cool. Awesome.
Cool. All right. Any other questions? All right. So I think I'll hit stop record now.
Cool.